Welcome to The Explainer. Today we are digging into the code that runs pretty much everything in our lives. It's a story all about zeros and ones, but you're going to be shocked where it actually comes from. Hint, it's not a lab, it's ancient philosophy. I mean, just think about it. Your phone, your smart TV, your car, it's all built on this incredibly simple system of just 2 digits. But why? Why binary? We count using 10 digits, 0 through 9, so why do our computers get by with just 2? Well, the answer isn't simple. It's this amazing journey that connects ancient philosophy, a bit of divine inspiration, and some absolutely brilliant engineering. So if you're thinking the story of binary starts with some engineer in a lab somewhere, you'd be wrong. Our first stop isn't with an engineer at all, but with ancient Chinese philosophy and a German polymath who literally saw the divine in numbers. Okay, so check out this incredible cross-cultural connection from over 300 years ago. You have this French missionary in China, Joachim Bouvet, who's studying the ancient I Ching, this philosophical text all about the dualism of yin and yang. He starts writing letters about it to this genius back in Germany, Gottfried Leibniz. Now, the timing here is just unbelievable because Leibniz was already working on his own idea for a binary system. He gets these letters, he sees the structure of the I Ching, and a light bulb just goes off. It's a perfect parallel to his own system of zeros and ones. For Leibniz, this was way more than just a cool coincidence. He saw it as a universal truth. To him, the binary system was this perfect, beautiful metaphor for the Christian idea of creation. The number 1, that represented God, the ultimate unity. And 0? That was the void, nothingness. And from just those 2 things, God and the void, the entire universe could be created. It was, to him, divine mathematics. And you have to understand, Leibniz wasn't just an abstract thinker. The man was a practical genius. He co-invented calculus. He built one of the very first mechanical calculators that could add, subtract, multiply, and divide. He was so ahead of his time that he even imagined a future machine that could run on his binary system using, get this, marbles and a kind of punch card. We're talking centuries before it was possible. So Leibniz gave us the numbers, but for these zeros and ones to become the language of computers, they needed something more. They needed a brain. They needed logic. Fast forward about a century and a half, and an English mathematician named George Boole comes along with the missing piece. In 1847, he invents a totally new kind of algebra, but this one didn't use numbers, it used concepts, true and false. And this was the huge breakthrough. Boole realized that true and false could be perfectly, beautifully represented by Leibniz's 1 and 0. And here's how he did it. With simple little operators like and or, Boole built a system for complex reasoning. So for example, the statement A and B is only true, which is a 1, if both A and B are true. Otherwise, it's false, a 0. With just a few simple rules like this, all of a sudden, zeros and ones weren't just for counting anymore. They had the power to make decisions. They could actually reason. But here's the kicker. Like so many revolutionary ideas, it was totally ignored at first. His colleagues thought it was basically useless, calling it philosophically strange and having no mathematical significance. It was seen as a weird little game. It took almost another 100 years for the world to catch up and realize the incredible power Boole had just unleashed. Okay, so now we have the philosophical idea and the system of logic, but it's all still just theory, right? It's just on paper. How do you actually build it? How do you turn abstract logic into a physical working machine? The big challenge, then, was to find something in the real world that could physically be a 1 or a 0. You needed something that could switch between 2 states, nice and simple, and do it reliably over and over again. The first real clue came in 1886 from, of all people, another philosopher, an American named Charles Sanders Peirce. He was the one who first theorized that you could use electrical circuits to perform Boolean logic. I mean, it makes perfect sense, right? A switch has 2 simple states, on and off. The idea was just hanging there, waiting for someone to grab it. And the person who finally put all the pieces together was a 22-year-old student at MIT named Claude Shannon.
His master's thesis, written in 1937, is the stuff of legend. People have called it possibly the most important master's thesis of the century. I mean, can you imagine?
What Shannon did was prove, mathematically, that the on-off state of a simple electrical switch was a perfect physical representation for the true-false of Boolean logic. By connecting Boole's abstract system to practical, real-world engineering, he essentially handed the world the blueprint for the digital computer. The modern computer was almost here. It had a language, binary. It had a brain, Boolean logic. It even had a nervous system, electrical switches. But it needed one last thing, a way to get instructions and actually remember them. And the solution came from, yet again, a surprising place, the U.S. Census. An inventor named Herman Hollerith saw train conductors punching tickets, and it gave him an idea. He built a machine that could read data from holes punched into cards. This machine was so effective it took the 1890 census from what was an 8-year job down to just 1 year. It was a revolution in data processing. And his little company, it would eventually become IBM. And here's a fantastic bit of trivia for you. Hollerith's standard punch card had 80 columns. That 80-character limit became an industry standard for decades, and it's the reason why, even today, some programming style guides still recommend keeping your lines of code under 80 characters. It's a little ghost of the punch card, still living in our modern software. But putting data in was only half the problem. The computer needed a working memory. Early attempts, like these things called mercury delay lines, were super slow and clunky. The real game changer was the Williams-Kilburn tube. It basically used a screen, like a little TV, to store bits as tiny dots of light. This was the world's first random access memory, or RAM, because it let a machine instantly grab any piece of data from anywhere in its memory. And finally, on June 21st, 1948, all of these different pieces came together. A little experimental computer called the Manchester Baby used a Williams-Kilburn tube as its RAM, and it executed the world's first ever program stored in electronic memory. It took 52 minutes, but it got the right answer. This wasn't just a calculation. This was the moment software was born. So let's bring it all home. Why did binary win? Well, in the end, it boils down to its elegant simplicity. A two-state system, on-off, 1-0, is just physically easier to build and way more reliable. You have way fewer errors than you would with a 10-state system. It mapped perfectly to true-false logic, and that simplicity meant you could design incredibly fast and efficient circuits. It was just the perfect fusion of theory and engineering. It's really an incredible story. The digital world that we all live in wasn't just engineered. It was literally born from philosophy, theology, and logic. And it really makes you wonder, as we start looking towards things like quantum computing and AI, what new way of thinking, what completely unexpected philosophy is going to be the thing that defines the next great leap in technology?